Hello all. Today we are going to discuss our this year's IROS submission, Key Point Based Adaptive Visual Servoing for control of robotic manipulator in its configuration space. Our primary objective is to develop a better and more efficient method for vision-based control. Vision-based control is the method where visual feedback is used to obtain control error. In this video, the controller is trying to align the marker on the object or on the robot hand to the center of the image to achieve a grasping task. In this video, deformable objects like a cable and a sponge is manipulated to a target shape in the image space. So a cable is manipulated to the red shape. And then here, the sponge is manipulated to a red contour. In this video, a drone is trying to land on a moving shipping deck by following the position of the Aruko marker using a camera. So in all three cases, you can see the robots are using visual feedback to be manipulated. By using visual feedback to obtain control error, the robot can gather and utilize information that is specifically relevant to the task at hand, which can help it operate more efficiently and effectively in unstructured environments. This control method, as you can see from the videos, has gotten quite popular in the past few days and is used for tasks like position and manipulation and navigation. Now, visual servoing can be broadly divided into two categories, image-based visual servoing and position-based visual servoing. In this paper, we focus on the image-based visual servoing and won't be discussing the other one for the interest of time. There are two different setups for image-based visual servoing. The eye-in-hand setup, where the target object is fixed and the camera is moving, and the eye-to-hand setup, where the observed target is moving and the camera is fixed. Now, this is a very common eye-in-hand setup where the camera is attached to the arm. This shows the camera view of the initial feature positions, which are the colored crosses, and the reference feature positions, which are the colored circles. The goal of visual servoing is to align the two different feature points with each other in image space. Now, this block diagram describes the image-based visual servoing where a reference and a current feature position is added to the controller. The control error is between the current and the desired visual features P and P star respectively. The small v is the feature velocity, which is derived by combining the inverted image Jacobian, the control gain lambda, and the error. The image Jacobian relates to the velocity, relates the velocity of the visual features to the velocity of the target of the camera. In the next equation, we are getting the joint velocity by combining the robot Jacobian, the current joint position, and the feature velocity. Now we replace v from equation 1 in equation 2 to get equation 3. The robot and the current Jacobian with the robot and the image Jacobian along with the current joint position combined give us the combined Jacobian, which is the equation for visual servoing. In these two videos, we can see the equation at work. In the first video, we can see the movement of the arm. And in the second video, we see the camera view, how the current and the feature reference positions are getting aligned. Now, the magic of equation 4 is that it was formulated to help a manipulator work when the robot model is not known, which is often the case for soft manipulator. And also when the robot environment of operation is unstructured, visual servoing is much more robust than traditional control methods. However, in this video, it is an iron hand setup in action. The camera attached to the manipulator detects the objects using color segmentation and determines the shape and then navigates to the box to complete a pick and place task. Notice within the control loop, quite a few steps of image processing is happening. And also, as the camera gets closer to the object, the reflection is changing the appearance of the color, which is setting up for an erroneous feature detection. Now, this video is an eye-to-hand setup depending on an Aruko marker in the end effector position. This pipeline completely is reliant on the marker, and at any point, for any reason such as lighting condition, if the camera fails to capture the marker correctly, control failure is inevitable. There is another shortcoming for the baseline visual surveying method. Given a target position in an image space, a standard 2 degree of freedom arm can reach the position in this configuration, which we will call elbow left, or in this configuration, which we will call elbow right. If the intended configuration is either of them and the other one is achieved, that defeats the purpose of operating the robot in an unstructured environment. Now, we attempted to remove all the shortcomings discussed in the previous slides in our prior work, skeleton-based visual surveying. Here, we aimed at generating natural features and control the robot in configuration space. In this method, we extract a skeleton of the robot configuration using depth image and process it. The blue line along the configuration is the processed skeleton. We then fit a B-spline curve to the skeleton. The red curve along the arm is the fitted curve. The coefficients, also known as the control points of the B-spline, are then used as the natural features to control the arm. In this video, the robot is controlled using the yellow control points. Here we can see control points are distributed along the body of the robot, thus allowing it to be controlled in its configuration space. This video shows our prior work was much more robust than the baseline method. However, to extract a skeleton, we need to spawn both RGB and depth images at the same time, which leads to heavy image processing. Due to the inconsistency of depth images, the features are quite noisy, as you can see from the graphics. Also, to restrict the skeleton to the configuration of the robot, we need to use Aruko markers at the base and the end effector of the arm. This means that even though we are using natural features, the method is still computationally heavy and still reliant on fiduciary markers. So in search of better natural features to get control error, we decided to look into key point detection for human pose estimation. Key point detection is a very popular approach these days in computer vision to solve the human pose estimation problem. So what are key points? Key points in a human pose estimation are the pixel coordinates of a point on a body part in the image. The dots on the human body parts in these images are the key points which we are talking about. Now, there are quite a few established data set which identifies and labels different human body parts as key points. This table depicts the level of labels of body part key points in Microsoft COCO dataset, one of the most popularly used dataset. This figure is a human pose estimation using the COCO dataset. This table lists the body part key points in MPII dataset by the Max Planck Institute, another popular such dataset. This figure is a human pose estimation using MPII. Now, COCO and MPI are just datasets. In the past years, there has been significant amount of progress in the deep learning field to use these datasets. One such field is Detectron 2. This is a video of real-time pose estimation using Detectron 2. This one is OpenPose, another very popular deep learning model for human pose estimation. Now, inspired by key points in human body parts, we started looking for similar datasets for robot manipulator. And lucky for us, not too long ago, NVIDIA Labs and CMU Perpetual Lab collaborated in creating a deep learning framework to identify key points on a few popular robotic manipulators like Baxter UR5 and Panda ARM. They call it Dream Pipeline. However, their motivation was not robotic pose tracking, but to use the robotic pose in the image space to accomplish one-shot camera extrinsics. So if you see this part of the block diagram, 2D key points on the image is passed through a PNP solver along with forward kinematics and camera intrinsics to get the camera extrinsics. Now to get here, Dream created a very large data set, but in simulation environment, where they identified key points on each and every joint locations of the SAID manipulators. This dataset is then trained with an encoder-decoder model to obtain a vector of 2D key points, n number of key points, as in n number of joints. They had an inference test set, and here you can see that using Dream train model, different joint positions are detected in real robots. However, when we tried to infer similar joint key points in our Franca arm, in our experimental setup, in certain configurations, all the joint key points were not identified. So this led us to create our own data set. Now, our proposed method has 4 major parts, and the first one is to identify the correct feature points on the robot body or key points. We use the distortion-free projective transformation of a pinhole camera model, which is given in this equation. If we have the camera intrinsics, which is consisting of the focal points and the principal point or camera center, and the 3D world coordinate of a point, in our case, a joint location on a robotic arm, the camera is extrinsics, and an arbitrary scaling factor for transformation from world coordinates to image space, we get our pixel coordinates of the point PW, which is the 2D projections of PW in image space, which are our potential key points. This is the overall pipeline for the key point identification and the dataset generation. We get current joint states from the ROS wrapper of the robot of the Franca arm that we got. We pass it through a forward kinematics pipeline to get the 3D joint location. We receive our camera intrinsics from the ROS wrapper of the camera node. And we receive the camera extrinsics from our old friend, NVIDIA Dream. Combining these three, we get our 2D projections. We save this 2D projection along with the images in a JSON file as annotations. We move the robot in arbitrary configurations to create collect a data set with images and corresponding JSON files. We have open sourced this data collection pipeline for other arms too. Sample image with annotated labels look like this. We have 10 key points and on the robot and annotated 10 bounding box. And this is how the JSON file, sample JSON file looks like. The next phase is to train a network using the dataset that we have created. We're using Keypoint RCNN model for training the network. Keypoint RCNN, which is an extension of Mask RCNN, is the state-of-the-art algorithm for keypoint tracking in human pose estimation. The above block diagram is the Keypoint RCNN architecture modified for our dataset. The model is run on a backbone of ResNet50 FPN, which is a feature pyramid network, which extracts features in different scales and resolution. The regional proposal layer predicts the rough location of the number of objects detected in the feature map that we are getting from the backbone layer. The feature maps are usually different in size. Different feature maps are different in size. So they are passed through an ROI line layer to get all the feature maps in the same size. Now, when we get the fixed size of feature maps, we pass them through two layers of convolutional network to get the heat maps of key points, the bounding boxes, and the scores of each key points. The loss function we use here is softmax, and because key point RCNN is a multi-class classification and not a binary class classification. Once training is completed, we evaluate the model using the COCO datasets evaluation matrix. The output for one image inference looks like the above, where key points can be predicted more than once. So you can see there are more than one labels predicted here. We use the score above 0.7 to identify the best key points. But even then, you can see that there are multiple key points with greater than 0.7 values. So we use a method called non-max suppression, which uses the IOU threshold to keep the best candidate points. In our case, if the IOU is greater than 0.5, the key points are discarded. Why 0.5? Because the evaluation matrix gave us two possible IOU, of which 0.5 scores better than 0.75. This gives us the final predicted key points. In our experimental setup, now you can see for different configurations, we are getting good results. Now that we have predicted the key points, we pass them as measured and reference feature position P and P star, respectively, in an adaptive visual serving scheme. We calculate the feature velocity VP by combining a control gain lambda, the image Jacobian, and the error in equation 1. We obtain the joint velocity QR dot by combining the robot Jacobian and feature velocity in equation 2. Replacing equation 2 in equation 3 to get the current joint velocity. Now we combine the robot Jacobian and the image Jacobian to get our combined Jacobian, JC hat. Now, in an adaptive visual serving scheme, we estimate this combined Jacobian online rather than giving it a fixed interaction matrix. We collect the last n samples of applied joint velocities, Q dot, and the change in image features, which is P dot, capital P dot. The collected sample or window of this visuomotor pairs of data is then used in a single shot least squares optimization to obtain adaptive updates for each row of the JC hat. The correction term or least square optimization is shown in equation 2. The adaptive updates are added to the current estimation as shown in equation 1. We initialize the adaptive scheme by providing a system a small excitation velocity trajectory to estimate the initial combined Jacobian or adaptive scheme. This graphics shows that initial window where the initial Jacobian is getting estimated. This window size is very important. Large window sizes prevent sudden spikes in robot joint velocities, but increase the convergence time of the estimated Jacobian. Smaller window size are very susceptible to noises. So if the features are noisy, we need larger window size. In our case, our window size is very small because of the lack of noises in our features. Here we have our overall pipeline for the control algorithm, where we are training the dataset through keypoint RCNN, and we are passing our trained model through a goal image and the current images to get our predicted key points, use them as our feature control features. We get our feature error, pass it through our visual servo controller, estimate our combined Jacobian online, get our joint velocity reference, pass it through our inner velocity control loop, pass it as our joint efforts to move the robot to its current position. And the loop continues. Summary of our proposed method. We identify key points on robot joint locations using distortion-free projective transformation of pinhole camera model. We build a pipeline to collect data with images and annotated key points as identified above. The data collection pipeline is open source for general purposes. We use the dataset to train a model to predict key points in real time using key point RCNN model with ResNet 50 FPN backbone. We use the predicted key points as control features in our adaptive visual servoing scheme. Let's discuss the experimental results. Now, let us discuss about some experimental results. The model error or the estimation error settles to a near zero steady state. The control error converges fast and smoothly for all the features. The input joint velocities are also pretty smooth. Now we compare our approach to the state-of-the-art skeleton-based method. Our method results in faster transient response due to less noisy and more robust features. The table shows a performance comparison between the two methods. The overall system rise time, that is the rise time of all the three control features when compared. The skeleton best has a higher rise time compared to our proposed algorithm. The settling time is also higher. The end effector rise time and end effector settling time is comparing only the end effect at the last key point and the last control points, which is also better in our proposed method. The overshoot is also higher for skeleton best compared to our proposed method. Now, in our cases, you can see that we are able to servo the arm to different configurations, even at the edges of the robot workspace. We are also able to see that the trajectories are smooth and repeatable for all those cases with very minimal noise. We were also able to servo the arm in 3D configuration space, but it came with limitations that a lot of configuration could not be achieved, and the control gains are different for different experiments. So as a concluding remarks, we have identified key points on robot joint locations using distortion-free projective transformation of pinhole camera model. We built a pipeline to collect the data with images and annotated key points as identified above. We open source the dataset pipeline at this link. We use the dataset to train a model to predict key points in real time on robot body using key point RCNN model with ResNet 50 FPN backbone. We use the predicted key points as control features in an adaptive visual servoing scheme. The method is faster compared to the existing method with much less noisy features in comparison. We were able to servo the arm in variable planar configurations, including edges of workspace. The process is repeatable, and we were able to servo the arm in different spatial configurations. However, the configurations we could achieve were limited. Using key points identified at the grippers, we aim to achieve grasping tasks using visual features in our future works. Um, we noticed that the problem with achieving perfect convergence in 3D Cartesian space could stem from lack of data for certain configurations. In future, we plan to expand the dataset as well as improve the network to curb this. Also, for better performance in 3D Cartesian space, we are aiming at using depth information as a potential control feature. Also, there could be cases of occlusion which we haven't handled in our current method, and for such scenarios where the manipulator is facing occlusion, we plan to utilize NERV for an extended version of it for the same. So overall, this is our key point based adaptive visual servoing to control the robot in a configuration space. Questions?